Hello. In this video I'll go through steps to measure JFET, pinch off voltage and zero gate voltage drain current. These are the main parameters used in determining proper biasing for the transistor. Now, when it comes to proper engineering, ideally you would design your circuit so it doesn't depend on these parameters, and they can vary a lot, but in this case, for example, if you want to achieve certain response from your amplifier, example of that is Fetzer valve that tries to mimic response of a valve tube. To get it depends on knowing these parameters so you can select proper components. So and actually this circuit here, this setup here is from their website, runoff groove. So let me just move this aside and show you the circuit. Okay. Here it is. It's quite simple circuit. There's a very similar circuit that I got from EDN website, which is essentially exactly the same. I'll go through runoff groove one in more detail in a moment, but they work on the same principle. This one is just a bit more complex and kind of it's not really necessary. It's the same thing essentially. So the circuit only has two resistors. Here it's say 10 mega ohms. I use 10 mega ohms and 100 ohms, and let me go through that real quickly. It has a switch here that you can change whether you're gonna measure pinch off or IDSS on your digital voltmeter, and it measures a voltage, and based on that you can get the parameters. So let's see how this actually works. So see, when the switch is in this position to measure IDSS, what happens here is, here this is shorted, so essentially this takes out this large resistor out of the circuit, and gate and source are shorted, right? So that's what it is, what IDSS is, zero gate voltage drain current. So this is zero voltage drop, so all the current goes through this 100 ohm resistor. So when we measure the voltage between these 2 points, we will get roughly 1/10 of a current in milliamps. So if you think about it, if this shows 1 volt, that just means that there is a current of 1 times 10 milliamps going through the resistor. Okay, so in the other position, this is shorted, ignore this. So this takes out the resistor out of the circuit. So what happens here is that this is here ground, and pinch off voltage, there is some leakage current going through the resistor, and it's really small. It's than 1 nanoamp or even less, and that would cause a drop here of just 10 millivolts or something like that, but that wouldn't be enough to cause the transistor to turn off. So what will happen, there will be very little current here, but just enough to drive JFET to turn it just about to be turned off. So it will be very, very close. This voltage here will be very close to that pinch off current. It won't be exactly pinch off voltage, but it will be very, very close by. So I mean, we could go and buy some commercial products for this, but in all fairness, most of them don't even measure JFET characteristics, and even those that do, most of the time they don't really have the right range for measuring these parameters, you know. So I have a bunch of different resistors here, but what I'm going to measure is this BF256B. Now, this is not really what you would exactly associate with audio designs. I have more commonly used the J201, and that one is roughly in, it's nearly in all schematics that I could find online. But today they're coming in these tiny, this tiny package, and I'm not gonna bother. I can solder them, but I won't be bothering with that today, and I'm just gonna use these ones. If I look at this, you know, if I look at the characteristics, it's no wonder that J201 is so popular. I mean, it has very tight characteristics, so pinch off voltage is between minus 0.3 and minus 1.5, and you know, IDSS is 0.2 to 1 milliamp, which is great. And in your circuit, most of, like, all of them will work if you design it correctly, especially running from 9 volts, you know. This one has okay characteristics, so it is between way wider characteristics, so it's minus 0.5 to minus 8, and pinch off voltage, and IDSS is between 6 and 13 milliamps, quite you know, wider range of parameters. But you know, if I look at this source from process 50, for example, and if I look at one very old Fairchild application note for selecting JFETs, you know, how do you choose proper JFET for application? And general purpose amps, P50 process is, yeah, maybe there is still hope for this transistor, and you know, low frequency, low noise amp. Maybe I can get away with this BF256, but like when I was looking for JFETs, my supplier, local supplier, doesn't really carry many, so I got all I could, at least in true hole configuration package. So this is quite old application note. It says 77 here, so, but I'm pretty certain this is still relevant. So if I look at part numbers and process application recommendations, so these are like, none of these I don't think are manufactured any longer. But if I look at this P50, you know, you get primary and secondary choice for various things. So for general purpose amplifier, it's primary choice, you know. J201 is process 52, sorry. So it is, you know, primary choice. So, you know, it might work, and I'm pretty certain it will work, but in reality, there's so few these true hole devices that I'd say just take all that you can get and try them out, and in the end of the day, all that matters is the sound you get out of it. Here, just before I start testing them, I'm just gonna take a note of these parameters to make sure that I'm getting values that are within the range of values. So, you know, -0.5, -8 for pinch off voltage, and 6 and 13 milliamps. Okay, I'm ready to test these. I breadboarded this. I don't have here toggle switch, so I have DT here. So when it's easy to see when you have a toggle switch, what are you measuring? I added 2-color LED to show me what am I actually doing. So I set it up this way so I can easily plug this out and replace this transistor. Here's my 10 mega ohm resistor, 100 ohm resistor. Everything is wired up. So I did mark my, I don't know if you can see this, I did mark my transistors with Roman numerals. Oh, okay, number 1. So I'll just plug this one in. Pin out is important, so I have gate, source, drain. So this is gate, source, drain. So yellow is gate, blue source, and red is drain. Just so it's easier for me to know where the things are. Let me start measuring. So I'll plug in battery. Turn on the digital multimeter, and let's go through this. So when light is green, LED is green, I'm measuring pinch off voltage, and let me write down the values so I don't forget. BF256B. I'm just gonna measure 5. This is going to be milliamps and volts here. Okay, let's do this. So pinch off voltage 3.16, minus 3.16, but I'm not going to put minus anywhere, negative sign. So let me just switch. Red, I'm measuring IDSS, and see, this is like 9.84 milliamps, because this is 0.9 times 10. Okay, so let me quickly go through the rest of them. Okay, what does that look like? Not too bad. And they have pretty similar parameters. How does this look like compared to the datasheet? Yeah, they're within the range as you would expect, right? So the next one I have is I have J112, and that one is not even close to being used in audio. But let me measure the parameters, and I'm sure I can work out something with that. Okay, let's look at these. Okay, let's look at J112. First of all, let's check the pinout. Okay, pinout is reversed from BF256B. Okay, that's good to know. And let's see some of the parameters, what to expect. So 112 here, expected pinch off voltage, yeah, -1 to -5, and IDSS minimum is 5 milliamps. Okay, what's the maximum? I don't know, but could be anything, huh? Okay, let's see what we're gonna get by measuring this. So this time I used a bit better marking so I can actually see that. So let me plug it in. Okay. 373. Oh, is this 48? Let's call it 47 milliamps. 47. Okay, let me double check with the data sheet. It didn't say anything about maximum current, and I can actually see that it can go anywhere really. See here it's 40 milliamps, so I'd say that's could be anything really. Let's carry on. quite a big difference for these two part numbers in terms of parameters. So we'll see how that works out when we plug this into Fetzer circuit calculation. So what I'm going to do now is I'm going to breadboard this Fetzer valve effect, and it's designed so the effect is emulating triode response or vacuum tube or valve response. This is a common source configuration with self-biasing, and here we have on input a low-pass filter that filters out anything over 20-something kilohertz, and we have to choose values here for source and drain resistors, and there is a calculator on the website that helps out with that once you know pinch off voltage and IDSS. So I'll be using that. A quick note, I'll be adding as this 22 nanofarad input cap to filter out any DC component, if any comes on input, and I'll just do away with this volume potentiometer, because I'll show that in a moment what the result coming from the website is for all the components. So okay, so what I have here is a printout from what I put in for the parameters in the calculator. So I have VP, IDSS, and I'll be using 9-volt power source, and what the calculator came up with is here 267 ohms for source resistor and 245 for drain. I actually don't have these, so I'll be just using 270, because that's what I have, 270, and I have 200 plus 47 ohms, so I have those, so I'll be using that. And here are some parameters that before I do anything, I'm just gonna check whether voltages are what says here. Drain current will be 565 milliamps, and here there is here's the amplification factor, so it's 0.5, so it's actually attenuating the input, so it's dropping by half actually, so I won't be really getting any amplification there. So the best I can hope is that the effect will color some of my sound and make it sound better, but here what I could do is put a booster in front of it or something like that, but I'll breadboard it just to demonstrate that this is actually working just fine. This is for BF256B, by the way, and I did the same thing for J112. And here I enter the parameters same way. What I have here is I have way lower resistor values, so I have 66 and 29 ohms, and the drain current, quiescent drain current, is going to be quite larger. It's like 33 and some milliamps. So when it comes to this, I would, if these resistors were larger, I would have to worry about power dissipation, for example, on them, because this is kind of a, I think my resistors are 100 milliwatt parameters for dissipation are 100 milliwatts, so they may just go up in smoke but it will be just fine for this low values here. And here the actual amplification is just 0.2, so it will kind of lower the input, will be actually 5 times lower, or it's going to be just 20% of the input on the output. What I have here, actually, I'm just wondering what the resistor I'm going to use here, and I think I have 22 ohms here, and here I think I have 47 and 22, so it's going to be 47, 22, 69 altogether. So let's see how that works. Okay, I breadboarded both of the circuits with both BF256B and J112. Here I still have my measurement, the circuit I use for measurements, but on this side, if I look at say BF256B circuit, here's my input capacitor, 22 nanofarads, 1 mega ohm and 33k ohm resistors. I think this one is 150 picofarads. It doesn't really matter, it just cuts off high frequency at something like 40 kilohertz. Doesn't affect our signal. Here I have in this case source resistor should be, we calculate 267, but here I have 270, and for drain I use two resistors, one 247 ohms, so it's 247, calculation was 245, not a huge difference, and at the output I have 47 nanofarads capacitor. Here I have J112 and input capacitor 22 nanofarads. This is exactly the same as before. 1 mega ohm, 33k. This case I used 220 picofarad. No difference at all for the audible spectrum because this cuts off over 20k and doesn't affect anything under 20k. Here it's J112. Here for the drain resistor, it said 29. I only have 22, so I use 22 here. For the source I have, I believe this one is 47 and 22, so that gives me 69. 66 was calculated, and 47 nanofarad output. So they're pretty much the same. I'm just gonna go and do the measurement now for source and drain voltage and see if that meets it agrees with what the calculations say on the website. So I'm just gonna do B256 first. I'm just gonna go and measure source voltage. So here it says 118. If I look at source voltage, it is saying 1.5 and 7.6. So this is quite a big difference from what I expected. And if I check my input voltage, let me see here, it's 908 So it's not a massive difference. It's not. I wouldn't expect that. I would have expected, based on the calculation from the website, to be around 1.5. So that's not the case. If I look at the drain calculation, it's around 8, but expected is 7.6. So I did my own calculation on this, and this is more actually what I'm getting, along the lines what I expect to get, but I'm not sure why does it differ on the website. So I'll do the maths later on when I finish this video. Once again, let me see for J112. What I have here is drain voltages. Did it pop out? Let's see. Let's see what's going on here. Oh, what am I doing? I need to do it this way. 8.6, and expectation here is 8, and for source 2.2. That's quite a big difference. Now for source 1.46. So when I looked at the website, what it said was that actual source resistor is the key to the sound, apparently, and the drain resistor is what is drain resistor here is what determines the optimal, point for that gives maximum headroom. But like that, I don't think that's correct here. At any rate, I'm not using the same values as calculated, but they're not that much off. So what I'm thinking is, as long as I keep the source resistor the same value and I change drain resistor, I should be fine. And I did a calculation, and 47 ohms should be good enough in this case, I think. So let me just swap that quickly. So what I have here is this gives me 0.9 before I hit the power rail. Here I have 1.5 volts before I actually hit the cutoff voltage. So I still have some room for manipulating this drain resistor, so I can still kind of have a greater value. I need to worry about drain source voltage and how that relates to gate source voltage, but like I should have some scope for improvement, I think, when it comes to that. But like what I'm going to do now, I'm just gonna hook up the jacks and play something through it, and let's see what we get. So what I have here, I wired up the effect. So here I have BF256B, and I just have it wired up so when it's red it's bypassed, okay, and when it's green the effect is on. So let me go with bypass effect. Okay, let's do it bypassed with the neck pickup. Let's engage the effect. Okay, it's a bit quieter, right? So let me put that on humbucker. Okay, so what I can do is, we expected that it would be a bit less loud, so it's quieter for sure, but like I can push it through a booster, for example. I have transparent booster in front of it, so I just turned it on, and let's see how it sounds with the neck pickup. Sounds much as expected, louder and nicer. Let's see if I now wire up. What I'm going to do now, I'm just going to wire up, instead of bypassing it on red, I'll have J112 wired up for that. Let me turn off the booster. Okay. Okay. So BF256. J112. And it is, as expected, a bit quieter. So let me just engage booster on top of this. Nice. And BF, again, just remind yourself. Let's put humbucker on. That's it, really. So both are working and both are giving, I'd say, pleasant sound, right? Okay, that's it for now.